Welcome everyone to the fourth lecture of Professor Bruce Watson on vector lattices with a view to applications in stochastic processes. Bruce, we look forward to your fourth and last lecture of this mini-school.
Thank you very much, and thank you for listening to me. Those of you who have joined and taken this tour through respaces, vector lattices, all the way through to getting to the starting point of stochastic processes in the respace setting. And in this lecture, we will actually, and this is the fourth of the lectures, we'll actually get to the point where we are starting to look at objects which have relationship to stochastic processes and are the first building blocks of those. And unlike the previous lectures, I'm going to start this one with some of the old well-known material on probability spaces and conditioning, because that is where we need to build our structures. And that's the template of where we're going. So I'll remind the listener that probability space is a measure space. So that consists of a set, omega in our case, F, a sigma algebra, and mu, a measure. And we assume that the measure is normalized so that mu of omega is 1. And that's what makes it into a probability space as opposed to an ordinary measure space. The fact that the normalization of mu is such that mu of omega is 1. And for most of stochastic processes, one takes as your random variables elements of one of the LP spaces, and over a probability space, the largest of your LP spaces is L1. The expectation of a random variable, F, so your random variable is an integrable function. The expectation of it is the integral of your random variable over the set omega with respect to the measure mu. And we can also think of this expectation in a slightly different way as a map from L1 to the subspace of L1 of functions which are in L1, but the sigma algebra now is made up of the sets of measure 0 and their complements. In other words, these are the almost everywhere constant functions. And this is a subspace and sublattice of L1 omega F mu.
Sorry, Bruce, can I ask a question before you move to the next slide?
Yes.
The expectation, what kind of object is it? Is it also a function?
Well,
it's not completely clear from the integral.
Well, that's the one in point 3, it looks like a number, but your numbers can also be interpreted as AE equivalence classes in your L1 space because you are working with respect to a finite measure. So you can think of it as conditioning over, if you were to not consider the almost everywhere character, you would be conditioning over the sigma algebra consisting of 2 objects, the empty set and omega.
Right.
So those are your constant functions.
Thank you.
So it has 2 interpretations. And when you want to look at your expectation as a special case of conditioning, you should think of it as a function, not as a number. So our next step in the process is to consider conditioning. And here you have a sub-sigma algebra, let's call it sigma, of your original sigma algebra F. And we have a random variable F, little f, and we want to condition that with respect to sigma. So we hope to find, and we denote it by EF given sigma, and for convenience in the formula, we're going to write it as capital F. And we want to have capital F to be measurable with respect to the small sigma algebra, sigma. And when we average over each one of the sets from sigma, that average must be the same for capital F as it was for our original little f. Note, our little f is not measurable with respect to the small sigma algebra necessarily. So this requires that your averages of capital F, in other words, the integral over A of capital F with respect to mu is equal to the integral over A of little f with respect to mu for all sets A from your small sigma algebra. Now, if you do a countable partitioning of capital omega, then you don't need any fancy tools and you can construct it, your conditional expectation. And I will manually do a case of this later on in the talk where it has some interesting other implications. But in general, your small sigma algebra, capital sigma, doesn't come from a countable partitioning of omega. It can be a far more complex object. And in that case, you need the Radon-Nikodym theorem. Because you can consider integrals over sets as measures, and then you use absolute continuity, etc., to get the Radon-Nikodym derivative of your measure, one measure with respect to another measure.
If I can ask a quick question here as well, why couldn't we take capital F to be small f?
Because small f has too much variability. It's when you look at the inverse images of the open sets under small f, they're allowed to be any object from your large sigma algebra F, capital script F. They don't have to live in your small sigma algebra. You want to find a function that is measurable with respect to your small sigma algebra.
Right, thank you. Thank you.
So what does this conditioning do? It takes you from your L1 space, omega F mu, to the L1 space where your sigma algebra has been replaced by sigma. So L1 omega sigma mu. And you can consider this as a subspace and sublattice of L1 omega, that appears twice there, sorry, L1 omega F mu. Furthermore, the conditioning map, is a positive order continuous projection onto L1 omega sigma mu, and it maps AE constant functions to AE constant functions. Now, there are some results that date back to the 1960s, mid-1960s, on the characterization of conditional expectation maps. And these are, they're mainly attributed to Douglas and Ander, who built the starting blocks of them. Rayo packaged it very nicely. Sadak did some order theoretic properties on it. So the following result, which I've given here, is actually quoted from Rayo. And this says that if we have a probability space, omega, I shouldn't have done this. I've switched around the algebra, the small sigma algebra and the big one on the slide. Sorry about that. A map T from LP to LP is a positive, if it's a positive contractive projection, so it maps non-negative functions to non-negative functions. Contractive, in other words, it reduces the norm of the function. So you take the norm of TF that is less than or equal to the norm of F, and projection. In other words, it's idempotent. So T of F is T of F. And it maps the constant one function to the one function. Then TF can be expressed uniquely, or can be expressed as a conditional expectation operator, or conditional expectation with respect to some sigma algebra. And this sigma algebra is uniquely determined by the map T. And Rayo attributed this specific version back to Sidak. However, the building blocks of this result were established by Douglas and Ando. Douglas worked with the L1 case and Ando for LP. And Douglas characterized the range spaces of positive contractive projection on the L1 piece, on L1 over a probability measure as conditional expectation operators. So he said that the range spaces of positive contractive projections on L1 are closed under order limit, and are vector sublattices of L1 are the range spaces of conditional expectation operators. And Ando generalized this to LP. So now let's see what we can do in the respace setting. So we remember that a respace is a vector lattice. So it's a vector space. It has a partial ordering. The algebraic and order structures are compatible, and it is a lattice. In other words, each pair of elements of the space has a supremum in the space. And the next object we need to revise briefly is the concept of an order limit. So if we have an Archimedean respace E and F alpha is a net, we say that F alpha converges in order to F if there is another net, G lambda, for some index set lambda, capital lambda, so that G lambda is downwards directed. And for each B, so that for each lambda in capital lambda, there is a B in the index set D of our original net, so that for all successors alpha of beta, we have that the absolute value of the difference between F alpha and F is less than or equal to G lambda. So if we think of ordinary sequences and we look at epsilons greater than 0, well, we can think of the F alphas as being the epsilon, and for each of those, there exists a capital N, that's your beta, so that for little n greater than or equal to capital N, that's your little n is your alpha, we have that the absolute value of Fn minus F is less than or equal to G lambda, which is our epsilon. So that's roughly how this fits together. And in this case, we denote, so if F alpha is order convergent to F, we can denote it by F alpha with a 0, an O underneath to F. And in the special case of an Archimedean respace, of a Dedekind complete respace, we can dispense with having different nets, different index sets for the two nets. So we can simplify the case slightly. So this led us to the following definition many years ago. It's actually 20 odd years ago now, when it was published. of a respace conditional expectation operator. And this was originally appeared as part of Wen Qi-Ku's PhD thesis. And we defined a conditional expectation operator in a respace, Dedekind complete respace with weak order unit, to be a positive order continuous projection T on E with range T, the range of T, an order closed subspace of E. I think we had it as Dedekind complete in our original version. That's equally good because we're working in a Dedekind complete respace. Our original version was in an Archimedean respace, but we're working with Dedekind complete respaces here. So we can work with an order closed subspace of E. And we call it a conditional expectation operator if it maps weak order units to weak order units. They're not necessarily invariant, but because it's a projection, you can always choose. There is one that is invariant under it. Okay. So we can refine this a little bit more. And since we're dealing with positive maps, we are going to define a map to be strictly positive if it's not only positive, but the only object from the positive cone that it maps to 0 is 0. And we call that strictly positive.
Can I interrupt you here again, Bruce,
yes.
very quickly? This is quite exciting. So you basically are abstracting from function spaces to abstract read spaces, this concept of conditional expectation, right?
That's correct, yes.
And is the idea that the larger the theory will lift to abstract read spaces?
Oh, well, quite a lot of stochastic process theory can be lifted to the respace setting. One of the interesting things is also when you take the respace theory back to probability spaces, we then end up working with the maximal domains on which you can define conditional expectation operators, filtrations, all of the objects. So you get the maximal objects for which they have meanings and are usable. Whereas classical probability gives you a restricted version of that. And we will see a little bit of that later in the talk.
Thank you. Yeah.
So let's just see whether this is a sensible definition and whether things work sensibly. Because certainly if you restrict yourself to L1 over a probability space, we should end up with something very similar to what should be a classical conditional expectation operator. So let's just verify that. So if we take L1 over omega F mu as our respace E, and we have mu as a probability measure, and if we take sigma as a subsigma algebra of F, then certainly our original space E is a Dedekind complete respace with weak order unit, the one function. This is under AE pointwise partial ordering. And if we set T of F to be the conditional expectation of F with respect to sigma, this is indeed a respace conditional expectation operator on E, and it takes the weak order unit, the one function, back to the one function. The converse is also true. So if we take T as a respace conditional expectation operator on L1 omega F mu, where mu is a probability measure, then there is indeed a subsigma algebra sigma of F so that T is equal to the conditional expectation with respect to sigma. So if we're working on a classical, in the classical setting, we get what we should get. Now, one of the early motivating ideas of looking at this was a piece of work in de la Charrière's and Mayer's classical text on probabilities and potentials, volume B of their 3 volumes, on theory of martingales, and I've given the exact section numbers there, where they were trying to extend to sigma finite processes martingale theory. And if one has a probability space, omega a mu, where mu is a sigma finite measure, then we can partition the space into a sequence of omega i's, each of which is mu measurable, and each one has positive measure. So now, if we take A0 to be the sub-sigma algebra of our original sigma algebra generated by this sequence omega I, then we can take the respace E of all the, sorry, something happened here, measurable functions, so that the second bracket got disappeared here, so that on each one of these omega i's, this is a bounded function. And we take our sigma algebras here, the AI's to be U, so the intersection of omega I with U, where U is in the original sigma algebra A. And here it can be shown that E is a respace under AE operations. Further, for each F in E, we can define P of F to be the average of F over omega I. And then indeed, P is a respace conditional expectation operator on E. And if F is in E intersection L1, then we have that T of F is indeed the conditioning of F with respect to A0. But we have that that L1 is not contained in E, nor is E contained in L1. Okay, this leads us on to the next concept. And this is how in the respace setting, we have a mechanism for extending conditional expectation operators to maximal conditional expectation operators, and to extend their domain to the maximal domain on which we can define a condition, do this extension. So, and we call this extension the T universal completion. And we say that we look at the positive cone of this extension, we call it DOM T, and we look at all the elements in the positive cone of the universal completion of our respace. Now, the universal completion of the respace is the respace, it's the smallest respace containing your original respace, which admits the arbitrary suprema of disjoint objects from your original respace. So you can take they don't have to be countable or anything. You can take a family of objects from your original respace. So long as they are disjoint, you can form their supremum in the universal completion. And the universal completion is the smallest respace, which allows that. So what do we, so we take as the positive cone of our extension to be the elements of the positive cone of the universal completion of E, so that there exists a net upwards directed. The net comes from the positive cone of E, so the F alphas that are the elements of the net come from our original space, E, the positive cone of it, and they must have supremum F in EU. And we need that T of F alpha has to be bounded in EU. So this collection of objects forms a cone, and we form the respace built from that cone. So Dom T is the cone of our new space, the positive cone of it, and we form our space by taking differences of objects from the positive cone, and we call that E hat. E hat is a Dedekind complete respace. It contains our original respace as an order dense subspace. E hat has a weak order unit. All the original weak order units from our original space are also in there. And it's also a convenient term to denote E hat by L1T because it behaves very much like L1 in the classical sense. And it has a direct connection to L1 as well, which I'll talk about. The classical L1. So that's how we extended the space, but we haven't talked about how we get our conditional expectation operator defined on that. Well, so if we take an F in the positive cone of E hat, then we know there is a net F alpha in the positive cone of our original space E, with T of F alpha bounded in EU, and F alpha having supremum F and upwards directed to F. Then, as T F alpha is upwards directed in E, and it's bounded in EU, it has a supremum and or an order limit in E in EU, and we denote that by T hat of F. You can go through the labor of showing that this is well defined because there are many ways we could have approximated F and formed it as the limit of such a net. So there are quite a few steps that are needed and certainly not shown here. And we extend E hat to the whole of the space E hat, again by breaking F into F plus minus F minus, applying T hat to F plus and to F minus, and then subtracting those two results. And it can now be verified that T hat is linear, it is order continuous, its range space is Dedekind complete or order closed in E hat. It is a projection, it is positive, and it maps weak order units to weak order units. So it is indeed a conditional expectation operator on E hat, and it is an extension of T. So let's return to our case of sigma finite processes. And I had defined them intentionally in a slightly deficient way. So now when we form E hat, this now gives us the extension to the maximal domain. And we find that this is exactly the space of measurable functions, so that the absolute value of F is integrable on each one of the omega i's. So in other words, F restricted to omega I needs to be in L1, omega A mu, for each I. And the conditional expectation operator T hat of F is exactly, if little omega is an omega I, then it gives us the average of F over omega I with respect to our measure mu, our probability measure, our measure mu. Okay. So our space E and E hat both have weak order unit, the identically one function, which is again a weak order unit, okay, which is not necessarily in our original L1 space as it was defined here, because the measure of our entire space omega could have been 1. The range of the generalized conditional expectation operator now consists of exactly the measurable functions, which are a constant on each omega I. And notably, this forms an algebra. And this happens for all, if our space E is T universally complete, then the range of T will always, in fact, be an algebra. And this is called an F algebra. Okay, so we now have defined the concept of conditioning in a space. And we've extended that to the maximal possible domain. And as we can see, even back here, this class of objects which you can apply this conditioning to is larger than your classical L1 in many cases. Even if you take your original space omega to be omega A mu to be a probability space, and you form this extension, you can end up, if you take a countable partitioning of that, E hat will be a larger space than your classical L1, strictly larger. And it is, in fact, the largest space you can extend your conditional expectation operator to. Okay, well, the next property that we're going to look at we will motivate it from our classical L1 space, where we have L1 over a probability space. And if we take sigma as being a sub-sigma algebra of F, and we denote our conditional expectation operator with conditional expectation of little f with respect to sigma, as shown here with its E F sigma, then we're writing this defining property that we had early on, now in terms of characteristic functions. So we have that the integral over omega of the characteristic function or indicator function of A times the conditional expectation of F must be equal to the integral over omega of the characteristic or indicator function of A times F over mu. Sorry, that should be a mu, not a u, for each A in sigma. And so this gives us, by the fact that conditional expectation operators are A uniquely defined, that the conditional expectation of the characteristic function of A times F with respect to sigma is the same as the characteristic function of A times the conditional expectation of F with respect to sigma for each set A from sigma. So this is a commutation property. Now, in L1 omega A mu, multiplication by a characteristic function of a measurable set gives us what is known as a band projection. And these band projections were mentioned last lecture by Anka Kaluch. And so they are a special type of operator on a space. Now, can we do a similar process in the space setting? So if we recall that in the second lecture, I talked about very special subspaces of respaces, which were called bands. They were vector subspaces, which were solid, and they were order closed. And in a Dedekind complete respace with a weak order unit, every band, every such subspace has a generator. And that generator can be taken to be a component of your weak order unit. Now we're going to look at those, the projections onto those bands, which are generated by components of the weak order unit, our chosen weak order unit, let's say E, which commutes with T. And we're going to take those that are also in the range of T. And we're going to show that those band projections commute with T. And why is this? And I'll also tell you why this is important in a few minutes as well. So we know exactly how to work out the band projection applied to an element from the positive cone of E. So if we take F in the positive cone of E, then the band projection generated by G applied to F is exactly the supremum of N times G infimum F. So it's the supremum of that object. Okay, which is the order limit of, this order limit looks a little bit strange here. It's not O minus, it's supposed to be order limit of the infimum of NG with F as N tends to infinity. But we also know that our conditional expectation operators are order continuous. That is one of their defining properties. So we can take order limits through the conditional expectation operator. So this says that if we apply T to the band projection generated by G acting on F, that is exactly the order limit of T of the infimum of NG with F. And as T is a positive operator, if we have the T applied to the infimum of two non-negative objects, that is less than or equal to T applied to the one object, infimum T applied to the other object. This is purely a property of positive operator. And well, we also know that T was in the range, G was in the range of T. So and T is a projection map. So T applied to NG is exactly NG. So we are left with, on the right-hand side, the infimum of NG with T of F. Now, if we take order limits again as N tends to infinity, the left-hand side of that equality there is exactly the band projection generated by G applied to TF. So what have we proved? We've proved that T of the band projection applied to F is less than or equal to the band projection applied to T of F. We can apply this exactly to E minus G. Remember, it's a component. So that comes in, and we can show that the band projection generated by E minus G is exactly I minus the band projection generated by G. So applying that, we arrive at the opposite inequality. Combining these two, we have that PTF equals TPG, where P is the band projection generated by G. And that's for everything in the positive cone. So we can apply it for a general F in E. We can apply it to F plus and F minus. We split them up, and we recombine them. And this gives us that PTF is equal to TPF. So we have the commutation property. And why is this important? This is the very first of the building blocks of what are known as averaging properties for conditional expectation operators. Because in a respace, you can decompose your elements in the respace as limits of sums of components of your weak order unit. And you can also characterize your F algebra multiplication by the starting definition that if you have two components of your weak order unit, their product is their infimum. So with those two, and then you extend by linearity, that gives you a definition for what you could think of as very similar to being simple functions, linear combinations of components of your weak order unit. Then you can take order limit to access all the elements in your space. And thereby, you have a commutation property for taking products, T applied to products of two elements in your space, and allowing one of them to move through like a scalar through the operator T. And that is the starting point of studying stochastic processes. Thank you.
Thank you very much, Bruce. Are there any questions from participants? There is none in QA, but if anyone has any question, we could also allow you to talk and ask a question. While they're thinking about a possible question, it is interesting that this reminds me a lot of what we do in category theory. So let me explain what I mean. So the concrete spaces from which you're abstracting are spaces of functions, right?
Yes, you start off with your ideas coming from function spaces.
Yes, yes. And so when you move, and then you move from a function space to your abstract read space, you're replacing functions with elements of the read space. Now, these functions in the concrete case have some algebraic structure, which is the read space structure. It's not only algebraic structure, though, there's also order structure, and so that's exactly what the read space captures. And in a way, that's exactly what we do in category theory, where we have some, let's call it a space of functions, but these functions do not necessarily go from one set to another. They could be going from various sets, so they can also compose when they match, when the codomain of one function matches with the domain of the other. Now, the algebra that these functions form is the algebra of composition, which in your case, it's not there because your functions don't compose since they are from one set to reals. But in a sense, the similarity is that there is some algebra still. And then we abstract it by looking at an abstract framework of functions that can compose. And sometimes we do want these abstract functions to also form even a vector space once the domain and the codomain is fixed. So from that perspective, I'm wondering about the following: whether one cannot fit the concrete case that you consider into some kind of category. So when you consider these functions from omega to reals, right? The elements of L1.
Yes.
Is there a reason? So there is a condition that defines what kind of functions we're allowed to consider, right? That's related to the measure.
That's right.
Is there a way of viewing the reals as also a measure space, and then having two measure spaces? I'm not sure if I'm using the right terminology. If I have two measure spaces, I define what a function between them is, and then when I restrict the codomain to be reals, and I get exactly the L1 thing.
Indeed, that's exactly what happens. And if one applies the T universal extension, the extension here, if you start off with a relatively small space, let's take L infinity over a probability space, or even possibly just you start out with your characteristic functions, your simple functions over a probability space, and you apply your T universal extension, you will get L1 if you take T as being your expectation operator. So if you take T as your integral over here, and you take your allowed, your Riesz space as being a very simple space, like, as I said, all you need are the simple functions over, so those are linear combinations of components and characteristic functions with respect to your sigma algebra F. And you define your integral map on those. And now you start working. And you do this process and you find your T universal extension. Your E hat is going to be your classical L1.
Yeah,
and
that's
so,
very interesting.
So, and the point is that yes, and when we do it for conditioning, for your general one, we are dealing with L1 as a Riesz space because we just need T to be a map back into our given Riesz space, or a particular subspace of it. So we have identified here, when we considered T as a conditional expectation operator, we actually used it. We didn't look at it as a map to the reals. We actually looked at it according to this last paragraph here.
So, yeah.
You're not really interested in it as a map from your Riesz space to the reals. You're interested in it as a map from your Riesz space back to your Riesz space with very special properties. So right. You can actually, as when you go over here, after you've done that, and you've thrown away the reals, you can even throw away the reals more, because what you really want is RT as your multiplier. You don't want the reals at the end of the day. And this makes this E hat into a module over the ring RT.
Okay, I want to get this right. So if you go back to the first slide that you were showing.
Where are we? Yeah.
So maybe that one.
This one?
Next one? Yeah, this one. My question has actually two layers. In the first layer, I'm not yet asking for abstraction. I just want to understand the L1 world before we abstract anything. So L1 here stands for measurable functions from omega to reals, right?
That's right. So that they are Lebesgue integrable. Yeah. And why do you need the Lebesgue integrability? That's a technical point, and
no, that's fine. So what I want to ask now is, if I have two sigma algebras,
yes,
omega 1 and omega 2, can I define a function between them to be measurable? Does it make sense to do that?
Yeah.
In such a way that when omega 2 is reals, then I recover back things that are in L1.
That's exactly when you take your sigma algebra on the reals to be the Borel sets.
Right. Okay, so now I could consider the world of all possible sigma algebras and all possible measurable functions between them, right?
That's right, yes.
And then say, okay, I don't want now my objects to be sigma algebras. I want them to be some abstract entities in such a way that the maps between these abstract entities form Riesz spaces. I mean, if I consider measurable maps from omega 1 to omega 2, do they also form a reed space? Or maybe something that looks like a reed space?
Okay, I can tell you some of what's happening where you're going. If you replace the sigma algebras by what are the components of our weak audience, these do not necessarily, they all will form a sigma algebra, but they actually have more properties than that. They're Dedekind incomplete. And those, once you know the components of your weak order unit, you in fact know a lot about what are your allowable conditional expectation operators. It doesn't uniquely define your conditional expectation operators, because just as in the probability case, you can have different underlying measures. So if you change your measure, what you will get out as actual maps for your conditional expectation are different. But if you know your original sigma algebra and you know your sub-sigma algebra, given that you know your measure, you will get a unique conditioning. So it's not.
I think I'm not asking about conditioning. I'm just asking if I have measurable maps from omega 1 to omega 2.
Yes.
Do they form?
Measurability is in turn entirely determined in terms of your sigma algebra. Yes.
Yeah. Do they form a structure that resembles a reed space? Well, probably you don't have addition anymore, right? You can't add functions from omega 1 to omega 2 anymore because it's just a sigma algebra.
So, okay, so you've got two sigma algebras.
Right.
Then you can define the maps between them. Well, you see, what you're actually interested in is some sort of vector space, free vector space built over those objects.
Okay. I see. But then if omega 2 happens to be reals, then I don't want free anymore, right?
Well, look, you can build such an object over, you give me a field or not even a field, so long as you have, you've defined what your type of multiplication you're going to allow on it is, and how you're going to add them, then you can extend from your sigma algebra to some form of linear combinations over characteristic functions of those in some abstract sense now, because that's what you're going to build. So how do you build a structure that is usable to go further?
Yeah, thank you very much. This is we should hopefully we will be able to continue this discussion. I have more questions.
I looked at some stuff. Serene came to give a talk at some point. And she was talking about objects which look very much like the totally abstract setting, but they had the same properties, if we go here, as the components of the weak order units.
Right. Yes, that I remember that discussion. That's also something to be followed up on. Yes.
And so the point is, if you have something with that structure, you can build a free type object over it, a free type lattice or vector space over it, first vector space, then build lattice structure, etc. So de facto, you can build a reed space over it.
Do you recover back the original reed space this way?
Well, so
if you started with a reed space,
no. You started with a collection of abstract objects that had the same sort of properties as the components of the weak order unit. So then you can build a linear combination type structure. You have a natural lattice structure on that, the components of the weak order units type object. It's some sort of Boolean algebra type structure. So the question is, how far can you take that?
And so the other question is, if you started with actual components of order units in an actual read space, would you recover back the read space this way?
Yes, you can.
Ah.
So that side you can do every. So the question is, now if I give you abstract objects that look like, that have the same sort of properties as components of the weak audience of a read space, can you build a read space over these entirely abstract objects?
Very interesting question. I think this brings us to the end of our session, but we will definitely continue these discussions and keep the community informed if we make some progress. Thank you very much, Professor Watson, for your lecture series. I don't think there are any further questions from anyone, so we can then conclude here.
Thank you very much, and thank you for listening to my talk. It's been a pleasure to give this series of lectures. And thank you again to NITheCS and Durab for chairing it and inviting me.
Thank you. It's been very interesting. Thank you. Thank you, everybody, for joining.